All right, so let's do this. All right, so now we're going to talk about exact ODEs and integrating factors. All right, so from calculus, we can do total differentiation of some function u of respect to x and y. And so here, doing total differentiation, if you remember correctly, is you do the partial with u with respect to x, dx with the partial of u with respect to y, dy. And then what you did is you solve for dx, dy. Let's let me do that with you real quick. So, and so we're going to set this equal to c, then du is equal to, if this is equal to some constant, we can say this is u. Du is equal to 0. And so let me show you how this works. So here I want to solve. So here I have this equal to, u is equal to this, which is equal to c. I'm going to do total differentiation on this. Okay. So if I totally differentiate this, here I'm going to have, so what's this? So here, using this formula, so du is equal to the partial of this with respect to x, which is 1 plus 2xy cubed dx plus 3, hold on, here we're going to take the partial of this with respect to y, right? Partial of u with respect to y. So if I did that partial differentiation, this is 0. This is 3x squared y squared dy. And then I'm going to solve this for dy dx. And so let's go ahead and do that. And so how do I see if I can do this correctly? So I'm going to move one side over. And so if I'm going to move this, let me see if I can not skip steps for you guys. Move one side over and then divide. And so this implies that minus 1 of 1 plus 2x in other words, y prime. You guys remember doing anything like this where you're given a function and you want to figure out what the derivative of y is when you know this and you do total differentiation vaguely? Oh, no, so du is equal to 0 because we set it equal to a constant. So we're not ignoring it. I just didn't explicitly say, hi, this is 0, which allows me to move this over to the side. Okay? Yeah. So here we have some function of x and y is equal to a constant, right? And I want to know what the derivative of y is, right? And so in order to do that, we just do total differentiation. Total differentiation is taught in calculus, but I find it's not taught well or often or at all. So some of you may or may not be as comfortable with this, but let me work through this as slowly and cautiously as possible. And we'll try to work you through all the mechanics of this. We should do at least 1 or 2 exact equations using this method. So here we're going to consider an exact ODE. So here, if I have some function of x and y plus another function of x and y times the derivative equal to 0, or in the case, another way of doing it is here, I have some function times dx and another function times dy equal to 0. It is exact if there is some function equal to a constant such that du dx is equal to this and du dy is equal to this. Okay? And so basically we're saying given this, was there a function that if I took a total differentiation that produced this equation, right? And that's the question we're asking here. When I ask, is it exact, is asking another way of saying, was there a function if I total differentiated it produced this function, right? And the answer is, and we want to show that this is equal to this. This is, to test this, it's just sufficient to show that we take this with respect to y. So we're going to take this function with the when it's not, and this one with respect to x. And so both of these should equal to du dy dx. Technically, that's not true, but since because technically the partial differentiation of dy with the partial differentiation of d del x technically is not the same as the partial differentiation of x times the partial differentiation of y. But for anything we're doing, we're fine. So don't worry about it, right? So technically you can't just freely swap these, but in everything we're doing, we're okay. So just ignore this, right? And so we get this. And so as long as it's exact, we can produce a solution. And let me show you exactly how to do this. And so here, given all this preamble, fancy math jargon of how we got to it, let's just do what the engineers care about. What are the steps I do to solve this problem? Right here. So we're going to test for exactness. How are we going to do that? We're going to take the partial of y, and we're going to set it equal to the partial of, so we're going to take the partial of m with respect to y, and if that equals the partial of n with respect to x, we're good. Then we're going to find the implicit solution by doing what? We're going to integrate. U is going to equal to this plus some ky, and we're going to integrate this with some L. Oops. Yeah, some this dx and this dy. Then we're going to solve for initial value problems. And so let me show you how to do this in practice. We should be able to get at least one done, maybe two. So let's do it. All right, so here, I want to solve this differential equation. And this is what your friends, this is what you show all your engineering friends scare them. It's like, oh, this is what we solved. And they're like, what? What is that? You just show them this disaster of a problem, right? But we'll solve it, and it's actually not that bad. So let's go through it. All right, so step one. So step one is we're going to test for exactness. So we're testing for exactness. So I'm going to take this will be my m, and this is my n. Okay, according to what I have on this page. Notice the only difference here is I've just multiplied everywhere by dx. So if I multiply by dx, dx, I get this equation. All right, so here, so what do? I take the derivative of m with respect to y. Okay, so let's do that. So here, I just get minus sine of x plus y. I'm getting a little crunchy. Hold on. Did I export this? I don't remember. Oops. Oh, not that fancy. I said not that fancy. Just a quick PNG is more than what I need. Yeah, save. Nope, I didn't. Perfect. All right, bye-bye. That's it. Goodbye. All right, so here, the derivative of this with respect to y is just cosine becomes minus sine, and then if you just do quick u substitution and chain rule, you get the same thing. So here we go. All right, so does this equal, question, does this equal the partial? Oops, I don't know if that look like a partial, not like a 2. Is this equal to the partial of n with respect to x? Well, here, if I take this with respect to x, this is 0. This is 0. This is minus sine of x plus y. And the answer is yes. Okay, so the answer is yes, so we can proceed. If it is not exact, if these do not equal each other, you're done, or at least for a second. I'll show you how to do integrating factors in a bit. So the answer is yes. So let's do step 2. So step 2 is we're going to do the following. We're going to set u equal to the integral of mx, so m, which is right here, cosine of x plus y dx plus ky. So here, plus dx plus some k of y. And so what am I saying? So u is a function of this plus some value of y, because that's not going to come out. Now let me explain. Let me do this problem, then explain where the math comes from. So if I did this here, so this is m dx, right? Then we're going to do it again for the integral of m dy. So here, this becomes sine of x plus y plus some function of y I don't know about. Okay. Here, if I take n and y, or with this respect to y, so here this will be 3y squared plus 2y plus cosine of x plus y dy plus some other function of x, which I don't know about. And here I have sine of x plus y. Let me write it this way. Let me do this part first. Plus y cubed plus y squared plus some function of L of x. Okay. All right. So what I do here, I found it was exact. Yes. And therefore I perform both these integrations to solve what u is, right? I want to find out what u is, because if I find out what u is, I can then solve for y. All right, so here, now I want to put it all together. U is equal to some constant, right? U is equal to some constants equal to u. So what is u? Well, u has to include this and then plus something of y. And then u has to include this plus something of x. And so what you do is you look at both of these and you try to put together an equation which satisfies this correctly. So here, I know I must have sine of x plus y. So let's just write that down. Sine of x plus y. I know I need that, right? So here I have sine of x plus y. And then I know I need to have, then I'm adding some function of y. Well, here's some function of y. So let's go ahead and add that function of y. Okay. And then I have to add some function of x, which agrees with this. But notice there's no x's here. And so here we're just going to, and so here we made this agreement. What's my function? What's my k of y? Well, it's this. It's some unknown function. What's my unknown function of x? Well, it's nothing, right? I can choose it to be nothing. And so I have this. And so this seems awful, right? It seems absolutely awful. And so here I have c equals the sine of y x plus y plus y cubed plus y. But notice what I've established here. I have established that this is no longer a differential equation. I only have y as an x. Now, is this implicit form? Yes. And most of you are going to be in implicit form in this case? Yes. All right, so let's do problem 3. So we have an initial value problem. And so this involves hyperbolic sines, hyperbolic cosines. All right, so here, we're going to let this be our m. We're going to let this be our n. And so the first thing we want to do, just as a reminder, so step 1 is to check for exactness. All right, so here we're going to take the partial of m with respect to y. If I take this with respect to y, I get minus sine of y, hyperbolic sine of x. And does this equal the partial of n with respect to x? And here, if I took this, here I get minus the sine of y, and then hyperbolic cosine just turns into hyperbolic sine. And so are these equal? The answer is yes, so this is exact. So since it's exact, we can move forward. And so we go to step 2. So step 2, we're going to do the following. we're going to take u is equal to the integral of, in this case, m. So our m here is cosine y sine of h dx plus some unknown function of y. And then here we're going to take our n, so minus sine of y cosine hyperbolic cosine of x, and then we'll do it dy plus some function. Hold on, let me clean this up. Even if I'm tired, I was going to give you horrible. There we go. And then some function of y. There we go. All right, so here we do this. And so once we do this, we just compute. And so when we compute this becomes hyperbolic cosine just becomes hyperbolic sine, or hyperbolic sine becomes hyperbolic cosine, just because they're just how that works. And so here I have cosine of h of x plus some ky, which I don't know about. And here I have sine goes to minus cosine. And so here this is just cosine of y, cosh, and we say it cosh or cinch with an H sound on it, out of y. When I merge these two together, we understand that this is the only thing that survives. And so here I have y is equal to cosine y, hyperbolic cosine of x, and that's equal to some c. Now, in this case, I want to find out what c is, and I'm given an initial condition. So here, just once you get it to this point, you're just going to type in cosine of 2 times the hyperbolic cosine of 1. So you just plug in an initial condition, that equal to c. You just crunch this through a calculator. These are two things you crunch in the calculator. You're going to get c is equal to minus 0. Oops. Hello. Minus 0.64. Okay. And then you can just write down your final solution here, that cosine of y equals cos of x minus 0.64. And this one you can actually kind of solve for y if you wanted to. You could say y equals the arc cosine of cosine hyperbolic of x minus 0.64. This should be a 1. Sorry, I put a 4 here. It should be a 1. Boop. 1. Okay. And so here you can get an explicit solution. Shouldn't that be? Oh, you're right. This should be ln of x. Okay. And when you go from this step to this step, just say, what function of y must I add? What function of x must I add? And if you don't need to add anything to make these two equal to each other, because u has to equal u, right? And so you're just trying to, and so this is the only thing that you need to really grab. If you had a constant, we could have a constant to make these equal to each other, but even if we had a constant, we're just going to kick it over to the side. Okay. All right. So that's how's that one. So I'll leave that up for a second. All right, so let's look at the next one. Then I'm all ready to go. All right, so let's solve this differential equation. So notice if we look at this differential equation, let's just see if we can make this exact. So if I take this with respect to y, I'm going to get del m del y is equal to -1. But I'm going to have del n del x is just equal to 1. And so these do not equal each other. So this is not exact. However, if I try multiplying by x squared, just real quick, and we're going to get the following equation. So here I'll have y over x squared dx plus x over x squared dy. And I'm going to set that equal to 0. Because here I'm just taking everywhere, and what have I done? I just multiply it through an x squared. And so if I simplify this, this becomes minus y over x squared dx plus 1 over x dy equal to 0. And notice here, let me do something. What do I want to do here? This is the total differentiation of the following. So dy over x. So here I can put this back together and do a total differentiation, right? Of d dx, right? If I total differentiate this, I'm going to get dy this and this dy because I don't know what y is. And so here, if I differentiate this with respect to x, and this is y. So that means d over x is equal to c, or y equals cx. And so what we get here is that by multiplying by something, I've taken something which I don't know is not exact, and then I produced something else. And what I produced here, well, in this case, isn't exact, but it's definitely solvable. And so we call stuff where we multiply everything across called integrating factors. There's better ways of describing it. I don't know why your book brings it this way. Some days your book does things slightly weird, which is fine, but I try to follow the way the book does it for the most part, if it's just for one section. For like chapter 3, no, it's either 3 or 4. It just does really weird stuff. And I'm like, no, let's resort it a little bit. And so here, we notice that multiplying by all these allows us to take something that we couldn't really solve it, right? So here we solved it. So we're going to use these integrating factors to reduce to exact form. So given the following, and now for whatever reason, they switch it to
Excuse
p.
me.
Go on.
Sorry. Can you go back to the last example, and can you explain the last part starting from the dx of y over x equals 0, please? I
Here?
did not follow. Yeah.
So here, notice if I did, so here, you're supposed to recognize this is the total differentiation of this. That's what you're supposed to recognize. If I took this with respect to x, so if I differentiate this with respect to x, I get y over x squared minus 1 dx. And so this is implicit differentiation. If I implicitly differentiate this, plus this with respect to y, well, with respect to y, I get a 1 over x dy. And so this is implicit differentiation. So then I can collect this and put it back into this. Okay. So let's see how I can say this politely. I don't expect students to recognize that implicit differentiation and then pull it backwards, right? I don't expect you to do that. I expect you to say, if I implicitly differentiate y and x, you can see how it became this. That's what I expect. Your book expects the other one. I'm like, nice try, book. So this isn't super useful except introducing the concept of why do we start multiplying stuff across, right? And the reason we multiply stuff into our equations, which are strange, is so we can solve things. And that's just, the book gives you this example to explain it. And so I was like, it's a nice example, I'll include it. but then I have that. So here, for whatever reason, your book switches it to P and Q. I do not know why. I legit don't know why. And I taught it one time, keeping it as M and N. But then when students went to look it up in the book, they got completely lost what P and Q was. And then so I went to teach it as, then I taught it next time as P and Q. And students just got less lost. They still a little bit confused, but they got less lost than the time before. I'm like, well, I can't help the book, right? So let's pretend I have an equation that's not exact. Then by multiplying by a factor of f, it is exact. And there can be many such things we multiply that makes this thing exact, right? So integrating factors do not necessarily make things exact. So what we did here, this is still not exact, correct? If I took this with respect to, no, this is exact. No, this is exact, right? If I take this with respect to y, I get -1 over x squared, right? If I take this with respect to x, I get -1 over x squared. So this becomes exact now, right? Everyone see how this became exact when I multiply across? Bigly. Yeah, this becomes exact. And technically, we could have solved it the other way, where we take the integration. We could have solved this the old way. And maybe next time I teach the class, I'll solve it the old way instead of just cheating. So this now becomes exact, and we can perform this operation, get to here. Here, let me hold on. Let me back up. I might get a little bit behind, but that's fine. Let's back up. If the book shows it's funny, doesn't mean I have to. All right, so let's back up. If you guys are unhappy with this, I'm okay with fixing it. Everyone okay up to this point? How I got to here? Everyone's good here. Then, is this exact? Yes, because if I take this with respect to y, what am I going to get? -1 over x squared. Is this exact? If I take this with respect to x, I'm going to get equal to -1 over x squared. So this is now exact. Since it's exact, I can say u is equal to minus dx plus some function of y. I can say u is equal to -1 over x dy, or positive 1 over x dy plus some function of x. These both give me y over x. Oops. Okay.
So if I understand, the last way you did it is all of these steps, you just kind of skip them with that notation.
Oh, the last way I did this?
Right.
The last way I did this is I just recognized that this is the implicit differentiation of d dx of y over x. You assume total differentiation, and then you do implicitly. That's what your book does. This is what I probably should do from now on, right? Because this is, it's just going back, doing exactly what you've been taught to do. Okay. So notice all these would make everything work just fine. Any of these. So we only need to find one of these factors. Isn't that how your book presents it? I could be full of, now you're making me paranoid. Let me double check in the book, and then we'll go forward. Because I don't think I would just do that on my own. I really don't. Yeah, that's what your book does. That's exactly what your book does. There's the fact that one's negative, one positive. When you differentiate the other one, it'll turn negative. So yeah, you're fine. Notice here when I anti-differentiate this, I'll get a -1, so that makes that positive, and this is positive. So yeah, that's what your book does, and then all of a sudden it switches notation to this P and Q. That's exactly what it does. All right, so anyways, by multiplying by something, you can create integrating factors. We still have another section to teach, guys, so let me move forward. But we only need to find one of these. And so you have two options, right? You can have and we're only going to introduce two things. We're going to find the following function r, and we're going to find r by calculating this big happy mess, right? We're going to take 1 over q. We're going to take the partial of p with respect to y, which you already would have calculated to see if it's exact, right? We already calculated to see if this was exact, right? And I already calculated this with respect to x to see if it was x. So these are already been calculated, right? We already have to calculate this. So we take this. If it's a function only of x, and it has to be only a function of x, then we say f of x is equal to e to the r. We take e to the integral of rx dx. Whatever that equals, that's our integrating factor. We multiply it by the whole thing. Then way back up here, this becomes exact. Okay, if and only if this is only a function of x. If it's not a function of x, you can't do this, right? If you cannot do this one, you're going to check this one. You're going to look for the following function r star. If you take 1 over p, and then here you're just switching the orders of this. If this is a function only of y, then you can find, oops, this should be f of y. Sorry, that should be a y. F of y. Then you can multiply across this, and then this becomes exact. If this is not only a this, you can't do this. Okay? So, with all that said and done, let's actually do one of these. All right, let me show you how it's done, because it doesn't make any sense unless we do it all in practice. So we're going to solve the initial value problem of this fine example of a hot mess of an equation. Something like way to describe that. All right, so let's do this. And let me see if I can explain it really close. It's easier shown than explained. So step 1, we're going to test for exactness. So I'm going to take this m and this n, whereas your book's going to now call it p and q. So I'm going to show you both. So here, we're going to take this partial of m with respect to y, right? Well, partial of m with respect to y is equal to e to the x plus y. Notice that this doesn't change at all. And then here, I need to do product rule. So it'll be plus y e to the y plus e to the y. Okay. Now I'm going to take this with respect to x. Well, this with respect to x is just equal to e to the y and nothing. Does this equal this? No. So this is not exact. Okay. Since this is not exact, we're going to kind of go to step 5, right? And step 5 is do an integrating factor. And so we're going to test both of these real quick. So r from our last page, and I'll just write it down for you, is equal to 1 over q of the partial of p with respect to y minus the partial of q with respect to x. But the partial of p with respect to x is the same as this, right? These are the same, right? Because n and q are the same, and p and m are the same. Why your book introduces a new notation, I do not know, but it does. And so here, this is also equal to the partial of q with respect to x. Why? Because it's the same thing. So let's go over this. So it's be 1 over q, which is right here, x e to the y minus 1. And here, what do we have? We have e to the x And here we have this, so right here, so e to the x plus y e to the y plus e to the y minus e to the y. Well, this is not a function of f of x only, right? It's just not. And so we don't use this one. So we try the other one. And this is r star. This is 1 over p. We switch the order. So del q, del x minus del p, del y. So here we just switch the order. All right, so let's do this. So here I'll have 1 over, I gave myself a little too much room, 1 over this, so it'll be e to the x plus y e to the y times, here we'll have e to the y minus this time e to the x plus y minus y e to the y minus e to the y. Now, at first glance, this looks like a big mess, but it actually cancels out decently well. This cancels with this. And so here, this is equal to minus e to the x plus y. And I'm going to pull out the negative sign. X plus y e to the y. And so this just equals to minus 1. Is negative 1 a function strictly of y? And the answer is sure, right? Yeah, this is an n. And so, yeah, sure. I mean, technically constants are functions strictly of only one variable. So technically you're fine. So you say, sure. And so here, oh, hold on, let me use this as, hold on. I didn't want to use a capital F, sorry. Just use the lowercase f, sorry. So this is a function only of y. Then what can I find? Then I can find my f of y by taking my integrating factor, e to the here, and we're going to put in f of y dy. Well, in this case, it's just e to the minus 1 dy, which is equal to e to the minus y. So this is my integrating factor. So what I'm going to do is I'm going to take this integrating factor. We're going to go back to step 1. So we'll say step 1, version 2, right? And this time we're going to put in the integrating factor. And so here, if I multiply everything by this, so I'm going to multiply everything by this. And so here I'm going to have e to the x plus y times e to the minus y, plus y e to the y, e to the minus y, plus, oops, hold on, dx plus e to the minus y, x e to the y minus 1 dy. I guess I could have distributed the same point. All right, so let's do this again. So this is our m, this is our, let's simplify it first. Hold on, let's simplify it first. All right, so here if I simplify this just becomes e to the x plus y times dx, okay? Because this will cancel that, this will cancel that. Plus, this will cancel that, so I'll have x minus e to the y minus e to the y to the minus y. So that cancels that, and then this is just here. This is all by dy equal to 0. All right, so let's test it again. Is this exact? And here, if I take this with respect to y, what am I going to get? So del m del y is equal to 1. And that's going to be equal to del n, so our n here with respect to x is also equal to 1. So we're good. This is exact. Now this is exact, and doing this integrating factor magically doesn't really change your equation enough that it's still the same. If it was true before, it's true now. Because I've multiplied it across to everything, and since it's 0 on the other side, it gets eaten. So now we can do step 2. And I really didn't leave myself much room, did I? That's fine. Let me cut this off so I have room. All right, so here it'll be u of the integral of e to the x plus y dx plus some constant ky. Here, if I take this with respect to x, I'm just going to get e to the x plus yx plus some ky. Here, if I do the other one, it'll be e to the x minus e to the minus y dy. And then here, plus some function of x. Now, when I crunch this through, I get xy plus e to the minus y. I got to anti-differentiate. Plus some function of x. All right, so now in our very first time, we have stuff that we're going to have to do. So yx and yx is in both. So we're going to write that one here. So we're going to say u is equal to yx. That's in both. Then here I have some function of y. Well, my function of y over here is just this. So we'll add that. So v plus e to the minus y. And then here I have some function of x, which is over here. So this will be plus e to the x. Let me set that equal to 0. Okay. Oh, we'll set that equal to a constant. Because whatever constant we get, we'll just kick it over. Okay, so here we have this. And so the main point of this problem, let me finish it real quick, and then I'll say what the main point is. The main point of this problem, we have 0, we have our initial condition, 0 and -1. So if I plug that in, here will be, hold on, x is 0, so 0 times -1 plus e to the positive 1 plus e to the 0 equals to c. That means c is equal to e plus 1. Okay, because this will be an e and this will be a plus 1. And there you go, there's your answer. Okay, so let me zoom out real quick and let me show what we did. Here we found something that's not exact. Well, since it's not exact, we try the two things from here. We try this, and we try this. And we want to see if either of these are functions of only x, if this is only of x or if this is only in y. So that's what we did. Here we calculated this mess. This does not simplify to be only of x. This, however, does simplify to be only in y. In fact, it simplifies just to be in -1. Then we use that to find an integrating factor. And here we get an integrating factor of e to the minus y. We found an integrating factor. So what do we do with that? We just multiply it across the whole thing. Multiply across the whole thing. We simplify, and then we just start all over. But if we did it correctly, this should now be exact, which it is, right? Oops. It's now exact. Now that it's exact, we just solved our exact equation like we've been doing. Okay.